then you go ahead and present your work, and we will allow people to ask questions while she's doing, so we don't have to wait until then. If you see something that you need to ask a question about it, then you can go ahead. So why don't you go ahead?
Okay, so my name is Christabel. A candidate for the master's degree in environmental toxicology in the Department of Environmental Science and Interdisciplinary Sciences. I did my bachelor's degree in biochemistry at Federal University of Technology, Owerri in Nigeria. So I'm a Nigerian, and after my master's degree, by God's grace, I hope to continue with a PhD degree in pharmaceutical sciences. Yeah. Okay, so back in the days, there is this ideology I used to have. If I go into the store to purchase, let's say, some food items, for example, cooking oil, if given the choice, I usually go for the cooking oil that is packaged in a transparent container. Because to me back then, what I think is, if I buy the one that's packaged in a transparent container, first of all, I'm able to see that what I'm buying is actually what's in the container. And second of all, I'm able to also see if there are any dirt or impurities in what I'm buying. But then I tend to forget that not all impurities are actually visible to the eye. So if you are asked the question, which of these cooking oils will you choose? The one that is packaged in an opaque container or the one that is packaged in a transparent container? But in case you don't have your answer already, by the end of this presentation, you will. Thank you.
And that is different option. You can use the arrow mouse there.
Oh yeah,
The
arrow mouse.
The arrow mouse.
Yeah,
Left, right?
Click anywhere on the slide. And use that.
Oh, thank you. So today I'm here to make an oral presentation of my thesis titled The Photochemical Effect of LED Lights on Various Cooking Oils. You might want to know what is the objective or what are the objectives of my research, and I'll tell you. My very first objective was to determine if any photochemical reaction took place as a result of exposure of some cooking oils to different colors of LED lights. Second, to ascertain if this photochemical reaction resulted in the production of new fatty acid metal esters or the removal of an existing one. Third, to find out if the newly produced fatty acid metal esters do pose any toxicity to the body. But before we continue, I would like to define some terminologies. The very first one is cooking oils. What are cooking oils? Cooking oils are plant, animal, or synthetic fats that is used in frying, baking, and other types of cooking. It can also be used in food flavoring and food preparation that is not involving heat. And as a result, that is why sometimes it's called edible oil. The main constituents of cooking oils are triglycerides. Triglycerides is a chemical compound that is formed as a result of the combination of one molecule of glycerol and 3 chains of fatty acids. So the picture on the left here, on my right here shows a typical structure of a triglyceride. Like I said before, it's made up of 1 molecule of glycerol and 3 chains of fatty acids. Let me give you a brief history of the LED light. The term LED stands for light emitting diode. It was first invented in 1927 by a Soviet inventor called Oleg Losev, but it was until 1968 before it was commercially produced. The very first color of LED light that was produced is the red light, and back then it was used as a replacement for the incandescent and neon indicator lamps that were found in laboratory equipment, TVs, calculators, watches back then. But with the recent ban on the production of incandescent lights, 2 options surfaced. The very first one was the CFL bulbs, the compact fluorescent lamp. At first, the CFL bulbs looked like the perfect replacement for the incandescent lights because it was more energy efficient, it was more durable, but it had some side effects. The very first one was that it takes a long time for it to shine to its brightest. And the second part was it contains mercury. So for example, if I'm handling a CFL bulb now and it mistakenly breaks from my hand, I'm automatically exposed to mercury. So with that in mind, the LED bulb came into play. The LED lights are safer, cheaper, more durable, and more energy efficient than the CFL and the incandescent light bulbs. What is a photochemical reaction? A photochemical reaction is a chemical reaction that is initiated by the absorption of energy in the form of light. So when a substance absorbs this light energy, it creates transient excited states whose chemical and physical properties differ from the original molecules. You will all agree with me that food substances are always exposed to light, both the natural occurring light and the artificial lighting. These food substances are exposed to light starting from their processing, their packaging, their transporting, and their storage. So when these food substances are exposed to light after a long period of time, it tends to deteriorate. This is called photodegradation. And it's been known that this photodegradation occurs in food substances that contain lots of oil and lots of fat. And after a while, when a food substance that contains lots of oil and lots of fat photodegrades, it tends to change color, it changes taste, and sometimes it loses some vitamins. So for the experimental section, we're going to discuss the experimental section in the following subheadings: sample collection, sample preparation, sample analysis, results and discussion, conclusion and recommendation. Sample collection, how we got our samples. Our oil samples were bought from a local market here in Houston called the Phoenician International Market. And 4 different oil samples were bought: the sesame oil, the olive oil, the grapeseed oil, and the hazelnut oil. For our LED lights, we bought them from an online store called Amazon. And 5 different colors were bought: black, red, green, yellow, blue. Sample preparation. So as soon as we got our LED lights, the first thing we did was to ensure to calculate the wavelength at which the lights they emit can be absorbed. So we did this using the handheld spectrometer called the UPR Tech MR350 spectrometer. So the picture above there is a picture of the handheld spectrometer. So from the results we got, it can be seen that the black light can be absorbed at a wavelength of 780 nanometers. The blue light can be absorbed at a wavelength of 432 nanometers. The green light can be absorbed at a wavelength of 551 nanometers. The red light can be absorbed at a wavelength of 648 nanometers. And the yellow light can be absorbed at a wavelength of 676 nanometers. Then for the oil samples, we needed to check to make sure that the oil samples can absorb these lights that we have got. So we checked this using the ultraviolet visible spectrophotometer, and below is a result of what we got. So from what we got, it can be seen that these oil samples can all absorb light that are emitted at a wavelength of from 200 to like up to 950. That's why you see that peak up there. So now that we know that our oil samples can absorb this light that we have, we decided to expose them. But before exposing them, we did something interesting. We collected 2 sets of each oil sample, and to one set we added 5 milligrams of titanium dioxide to it. You might wonder, why did we add 5 milligrams of titanium dioxide to it? That's because titanium dioxide is one of the active ingredients that is found in sunscreens. It's usually used in the production of sunscreen because it has high refractive index and it has strong UV resistant properties. So it has the ability to protect the body from the UV rays. So we decided to add this titanium dioxide to a set of our sample to see if it's going to prevent the absorption of light by this sample. So like I said before, we collected 2 sets of each sample. For the olive oil, we collected 1 set, and we collected 1 set with titanium dioxide in it and another set with no titanium dioxide in it. And we exposed all these oil samples in a rotary wheel to the light. So the picture there shows the samples in a glass vial in the rotary wheel, and the one at the extreme right there shows the sample being exposed to blue light in the dark room. Derivatization of samples. So because after exposure, we couldn't run these oil samples directly in the gas chromatograph mass spectrometer, also known as GCMS. So we decided to break the contents of these oil samples down to a way that the GCMS would be able to recognize it. So what we did was the fatty acid content of the oil samples were converted to fatty acid metal esters in a process known as transesterification. So the following procedure is the way we're able to convert the fatty acid to fatty acid metal esters. What we did was to collect 10 microliter of each oil sample. We put it into an amber bottle, which we called vial A. Then when we added 2 ml of a solution of 12% boron trifluoride that is dissolved in methanol to it. Then we heated the oil samples for 2 hours at a temperature of, we maintained the temperature between 65 degrees Celsius to 70 degrees Celsius. Then after 2 hours, when the oil samples must have properly dissolved in the methanol, we brought out the samples, cooled it, then we added 1 ml of saturated sodium chloride to it. Then we added 1 ml of trimethylpentane to it. When we added 1 ml of trimethylpentane to it, we vortexed it, then allowed the layers to separate. Then we carefully collected the upper layer. We added the trimethylpentane, 1 ml of trimethylpentane again. We repeated it 3 times. So at the end, we had a total of 3 ml of trimethylpentane that we added. So we collected the upper layer and discarded the lower layer. So the upper layer, to ensure that there are no traces of water in the upper layer, we passed it through a bed of anhydrous sodium sulfate. This is what is being shown in the picture. This is the bed of anhydrous sodium sulfate. We passed the samples through it into another vial, which we called vial C. And from the vial C, we collected 2 ml, which we ran in the GCMS. So this shows the equation, the transesterification equation. Like I said before, the cooking oil is made up of triglyceride. So a molecule of triglyceride reacts with methanol in the presence of a catalyst, which in our case was boron trifluoride, and it gave us fatty acid metal esters plus glycerol. The glycerol was the lower one, which we discarded, and the fatty acid metal ester was the upper one, which we took. But for your information, this reaction doesn't just go straight from triglycerides to fatty acid metal esters. It has some intermediates, which at first it goes from triglyceride to diglyceride, then monoglyceride, then the fatty acid metal esters. Now we have exposed all our sample and we've been able to derivatize them. It's now time for analysis. The very first analysis we did was the UV visible spectrophotometry. What we did was, after the samples have been exposed, we collected 2 ml of each sample, put it in a glass cuvette, and we ran it in the UV spectrophotometer. Then the spectrum we got, we compared it to the spectrum of the unexposed oil sample that we did earlier, that we got earlier. Another analysis we did was the thin layer chromatography. This was done using the Kamag high performance thin layer chromatograph. What we did was to apply the samples on a TLC silica gel plate. After application, the samples were then developed using a solution of 80 ml of hexane, 20 ml of ethyl ether, and 2 ml of formic acid. After development, we took pictures of the developed plate at wavelengths of 254 nanometers and 366 nanometers. But the pictures were not so, the bands formed on the TLC plates were not so clear. So to make them more visible, we decided to derivatize the TLC plates. So we derivatized the TLC plates using a freshly prepared vanillin solution. After derivatization, the plate was allowed to dry. Then we took pictures of the derivatized plate, now with the bands very visible. So we took pictures of the derivatized plate at a wavelength of 366 nanometer with the white remission light, with the white transmission light, and a combination of the white remission and transmission light. And after this, we also scanned the plate at wavelengths of 370 nanometers to 800 nanometers using the tungsten light. The final analysis we did was the gas chromatography mass spectrometry. the derivatized samples which we prepared earlier on, we ran them in the GCMS, and the chromatograms of the fatty acid metal esters were collected and studied. Results and discussion. The very first result we'll look at is the UV visible spectrophotometry results. So the first picture here shows the spectra of unexposed grapeseed oil and grapeseed oil that is exposed to green light. The unexposed grapeseed oil is the one in red, and the grapeseed oil that is exposed to green light is the one in green. From the picture, you can see that the two spectra are not the same, which is to say that after exposing this grapeseed oil to green light, something must have occurred, something must have happened to the grapeseed oil for it to come out as the spectrum. The same thing with the second one. The second one is the unexposed grapeseed oil with titanium dioxide in it, and the grapeseed oil with titanium dioxide in it exposed to green light. So the unexposed grapeseed oil with titanium dioxide in it is represented by the red line, and the exposed one with titanium dioxide in it is represented with the green line. So from the spectra, we can also see that they don't look the same. This gives us a preliminary proof that a photochemical reaction must have taken place after exposure. So this is a picture of our TLC results for the grapeseed oil. So looking at this TLC result, the very first band is the grapeseed oil that was unexposed. The next set of bands are the grapeseed oil exposed to blue light, the grapeseed oil exposed to black light, grapeseed oil exposed to red light, yellow light, and to green light. In each set, the one on the left is the one without titanium dioxide in it. The one on the right is the one with titanium dioxide in it. So looking at this picture, it's clear that the grapeseed unexposed band looks very different from the exposed ones, but I'll point out some differences. The very first difference your eye might catch is the color intensity. The color intensity of the bands formed in the unexposed grapeseed oil is increased after the grapeseed oil must have been exposed to different colors of light. You will also notice the formation of bands on top of each of the exposed ones. That shows that there is a chemical that was formed after exposure that is present here that wasn't present in the unexposed ones. Another thing we will look at is this first band up here, which is represented, that is the triglycerides. So if you notice, the distance traveled by the triglyceride band increased in all of the exposed ones when you compare it to the unexposed ones. This goes to show that there is new fatty acid that might have been formed as a result of exposure. So this is a TLC result for the hazelnut oil. Just like the grapeseed oil, the very first one is the hazelnut oil that was unexposed, and all the subsequent ones are hazelnut oil exposed to blue light, yellow light, green light, red light, and black light. And just like the grapeseed oil, we notice the increase in color intensity of the exposed bands when you compare it to the unexposed bands. We also notice that the distance traveled by the triglyceride band increased when you compare it to the unexposed hazelnut oil. Same thing applies for the TLC result for the olive oil. The color intensities increased in the exposed band when compared to the unexposed band. The distance traveled by the triglyceride band also increased in the exposed ones when you compare it to the unexposed one. And you would also notice for the black light, green light, and yellow light, there are some extra bands that were formed up here that were not present in the unexposed one. And finally, for the TLC result for the sesame oil, just like others, we can notice that there is a band that is formed up here in all of the exposed ones that it's not present in the unexposed one. Second, we will also notice the increase in color intensities of the bands. Third, we also notice that the distance traveled by the triglyceride band increased in the exposed one when you compare it to the unexposed one. That goes to show that a new fatty acid must have been produced as a result of exposure. We'll get a clearer result of all this when we look at the GCMS results. For the GCMS results, I use this to indicate fatty acid metal esters that are present, and the X indicates the fatty acid metal esters that are absent. The very first column there is the peaks. Each peak, 1 to 11, indicates a fatty acid metal ester that we encountered in this sample. The second column there is the C bond. The C bond, usually, the C bond tells the number of carbon atoms and the number of double bonds a particular fatty acid has. But because we're dealing with fatty acid metal esters, there is an additional methyl group to it. So a typical C bond that would have been interpreted as 16 carbon atom and 0 double bond, for fatty acid metal ester is being interpreted as 17 carbon atoms and no double bond. So for example, the peak number 6, that is 18,3, it means that that fatty acid metal ester has 19 carbon atoms with 3 double bonds. For the peak number 10, that is 18,1 triple, it means that the fatty acid metal ester has 19 carbon atoms and 1 triple bond. So when we look at the third column, which is the unexposed sesame oil, we'll notice that the unexposed sesame oil has a total of 8 fatty acid metal esters in it. But after exposure, 3 new fatty acid metal esters were produced. Another thing you also notice is that for fatty acid metal ester number 7, after exposure, it was totally wiped out. It was removed as a result of exposure. So let us see what are these fatty acids that were removed and the ones that were produced. So like I said before, the peaks represent the metal esters of these following fatty acids. The fatty acid that was produced, which is represented by the peak number 7, is 5, 8, 11, 14, 17 eicosapentaenoic acid. Eicosapentaenoic acid is a very important omega-3 fatty acid and also an essential acid in the sense that the body needs it, but the body cannot produce it on its own. So the body relies on intake of food for us to get, for it to get enough quantity of this particular fatty acid. So by exposing this sesame oil sample to the different colors of LED light just for 24 hours, this very important omega-3 fatty acid was removed. Then the second thing we also noticed was there were production of 3 new fatty acid metal esters, which are 6,6-dimethoxyoctanoic acid, the 17-octadecenoic acid, and the 9-dodecenoic acid. So for the 6,6-dimethoxyoctanoic acid and the 9-dodecenoic acid, from the researches we did, they do not have any reported negative effects in the body because they're used as food flavoring. But the same cannot be said for the 17-octadecenoic acid, which is a suicide substrate of a very important enzyme, the cytochrome P450 omega hydroxylase. I know we know the work of cytochrome P450 here, but I'll just try to remind us a little about it. The renal cytochrome P450 from the word renal is found in the liver, and it helps in the detoxification of xenobiotics, especially the harmful xenobiotics in the body. It detoxifies these xenobiotics by adding the hydroxyl group to it and making it more water soluble. So when we expose sesame oil to the different colors of LED light, and it produced just within 24 hours, it produced the 17-octadecenoic acid. This shows that some harmful, it has that oil, if consumed over a period of time, has some harmful effects that might have some harmful effects on the body. So for the GCMS result of the grapeseed oil, just like I explained before, the peaks represent the fatty acid metal esters. The C bond is the number of carbon and the number of double bonds in each fatty acid metal ester. So for the unexposed grapeseed oil, we have a total of 5 fatty acid metal esters present in it. But after exposure, we encountered 3 new fatty acid metal esters that were produced as a result of this exposure. And these 3 new fatty acids are the 15-methyl hexadecanoic acid, the 6,6-dimethoxyoctanoic acid, and the 9-dodecenoic acid. All these fatty acids, even though they don't have any reported proven negative effect in the body, but they go to show, they serve as a proof that that exposure of those oil samples to LED light do result in photochemical reaction, which goes ahead to create new fatty acid metal esters. Then for the olive oil, same thing applies. The unexposed olive oil has 5 fatty acid metal esters present in it, and after exposure, we encountered 5 other different fatty acid metal esters that were produced. And these other fives are the 15-methylhexadecanoic acid, the linolenic acid, the 6,6-dimethoxyoctanoic acid, the 17-octadecanoic acid, and the icosanoic acid. So apart from all the other fatty acids produced, do not have any reported negative effect in the body. But 17-octadecanoic acid, just like I said before, is a suicide substrate inhibitor of the cytochrome P450 enzyme. And finally, we have the GCMS results for the hazelnut oil. Just like the other ones, the hazelnut oil, the unexposed hazelnut oil has a total of 8 fatty acid methyl esters present in it. But after exposure, 2 new fatty acid methyl esters were encountered. And the same thing that happened for the sesame oil also happened here. The fatty acid that is represented by peak number 7 was totally removed as a result of exposure in this hazelnut oil. And what is that fatty acid? The fatty acid that is represented by peak number 7 is the linolenic acid, which is also an omega-3 fatty acid and also an essential fatty acid in the body. And also the two new fatty acid methyl esters that were produced are the 17-octadecanoic acid and the 6,6-dimethoxyoctanoic acid. Just like I said before, the 6,6-dimethoxyoctanoic acid do not have any reported negative effect in the body, but the 17-octadecanoic acid is a suicide structure inhibitor of the cytochrome P450 omega hydroxylase enzyme. So this is a picture of the chromatogram of grapeseed oil exposed to blue light and the spectrum of grapeseed oil that's exposed to blue light. So some of the peaks, there are some peaks that were formed here which we didn't take note of because for this research we're just concentrating on the fatty acid methyl esters. But there were other chemicals that were formed also as a result of exposure of this light, exposure of the oil samples to the light. So discussion. So the spectra from the UV visible spectrophotometer showed us that the difference in the spectra of the exposed and the unexposed first of all, gave us the first indication that something must have happened to our oil samples that were exposed. But we got a little bit clearer picture of what happened with the TLC results, which from the TLC results, we noticed one, increase in color intensity. We noticed some new bands that were formed. We also noticed that the triglyceride band, there was increase in the distance traveled by the triglyceride band, which indicates new fatty acids present in that triglyceride band. But furthermore, the GCMS result now gave us details of these new fatty acid methyl esters that were formed. And I would just like to mention them again. The new fatty acids that were formed were 15-methylhexadecanoic acid, the 6,6-dimethoxyoctanoic acid, the 9-dodecanoic acid, the 17-octadecanoic acid, and the icosanoic acid. All these fatty acids, like I said before, do not have any reported negative effect in the body, except for the 17-octadecanoic acid, which was actually produced in all of the oil samples except the hazelnut oil. Then the GCMS result also revealed to us that exposure of those oil samples to the LED light do not just produce new fatty acid methyl esters, but it also goes ahead to remove very important essential omega-3 fatty acids that were present in the original oil sample. So this here is the lipophilic potential map of 6,6-dimethoxyoctanoic acid. I used it for example because I noticed it was produced in all of our oil samples. So usually in a fatty acid, we have what we call the hydrophilic end and the lipophilic end. But for the dimethoxyoctanoic acid, due to the presence of oxygen molecules, which is represented by the red line, the both ends tends to be more hydrophilic than the middle end, which is very, very lipophilic. So in conclusion, based on the results of this research, we can say that exposure of cooking oils to different colors of LED light do result in the occurrence of a photochemical reaction, which will either create a new fatty acid or remove an existing fatty acid, or in some cases, a combination of both cases. So recommendations. Based on the having successfully completed this research, we had the following recommendations to make. The very first one is the idea of packaging cooking oils in transparent containers should be discouraged. This is to help ensure that the cooking oils are not always exposed to LED lights, because you agree with me that LED lighting is like the most common type of artificial lighting that we use nowadays. Then second recommendation is, if you already have a cooking oil that is transparent, that is packaged in a transparent container, do well to store it in places where it has little or minimal exposure to the light, and please discard it as soon as you notice that it has a change in color or a change in taste. And the third recommendation is, we would like further studies to be made on the reason why the addition of titanium dioxide did not prevent the absorption of light by the oil samples it was added to. And fourth, we'd also like we also like research to be done on the other chemicals produced, because for this research we just concentrated on the fatty acid metal esters that were produced, but there were other newly formed chemicals that were produced. So we'd like studies to be made on those chemicals and also on their toxicity in the body. So I would like to acknowledge my research mentor, Dr. Sally, my research committee members, Dr. Raman and Dr. Bhaskar. Thank you all for your help and support and guidance. I really do appreciate it. And to my research colleagues, Dr. Kevin, Dr. Esther, Duma, Angelica, Michelle, and every other person, especially my friends who are here to support me and listen to my presentation. Thank you all very much. I really do.
Turn on the light so we can.